On July 1, 2025, astronomers detected something extraordinary racing through our solar system at 152,000 miles per hour. This wasn't just another space rock, it was 3I/Atlas, a massive interstellar comet from beyond our solar system, potentially up to 20 kilometers wide and billions of years older than Earth itself. Unlike the mysterious Oumuamua that puzzled scientists in 2017, this visitor is showing clear signs of cometary activity, with a glowing tail stretching thousands of miles. Today we explore humanity's third confirmed interstellar visitor and what it reveals about the cosmos.
The discovery that shook astronomy.
The story begins with what seemed like routine observations at the Atlas telescope facility in Rio Hurtado, Chile. On July 1, 2025, the asteroid terrestrial impact last alert system detected a faint object moving against the backdrop of stars near the constellation Sagittarius. Initially designated A11PL3Z, this seemingly ordinary discovery would soon revolutionize our understanding of interstellar visitors. Within hours, follow-up observations revealed something extraordinary. The object wasn't following a normal elliptical orbit around our sun like asteroids and comets from our solar system. Instead, it was traveling on a hyperbolic trajectory with an orbital eccentricity of 6.15, the highest ever recorded for any object in our solar system. This mathematical signature could only mean one thing: the object originated from interstellar space. Amateur astronomer Sam Dean played a crucial role by discovering pre-discovery images of the object dating back to June 14, allowing scientists to calculate its precise trajectory. The Minor Planet Center received over 100 confirmed observations from telescopes worldwide within 24 hours, officially designating it 3I/Atlas, the third confirmed interstellar object ever detected, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019.
A colossal visitor from deep space.
What makes 3I/Atlas truly remarkable is its sheer size and speed. Traveling at approximately 152,000 miles per hour relative to our sun, this interstellar giant could journey from Earth to the Moon in just over an hour. Early estimates suggest the comet's nucleus could be between 10 to 20 kilometers in diameter, making it potentially dozens of times larger than its predecessors. When Harvard astronomer Avi Loeb analyzed the brightness data, he discovered something striking. The object reflects an unusual amount of light for its distance, suggesting either a highly reflective surface or enormous size. If its surface is dark like most asteroids, 3I/Atlas would need to be roughly 24 kilometers across to produce such brightness, making it a true cosmic giant. Unlike the enigmatic Oumuamua, which showed no clear signs of cometary activity, 3I/Atlas immediately displayed classic comet behavior. Observations from the Nordic Optical Telescope by astronomers David Jewett and Jane Liu revealed a diffuse tail on July 2, while the Teide Twin Telescope Observatory recorded a tail stretching 25,000 kilometers. This active behavior confirms 3I/Atlas is indeed a comet, not an asteroid.
A cosmic journey through our solar system.
3I/Atlas is currently positioned about 420 million miles from the Sun, roughly within Jupiter's orbit, racing inward on its one-way journey through our solar system. Its hyperbolic trajectory means it will never return. This is a single encounter that astronomers must maximize while the opportunity exists. The comet's path will bring it closest to Mars on October 2, 2025, passing within just 18 million miles of the red planet. Some researchers have proposed using NASA's Mars rovers to photograph the comet during this close approach, potentially providing unique surface-based images of an interstellar visitor. On October 29, 2025, 3I/Atlas will reach perihelion, its closest point to the Sun at approximately 130 million miles away, just inside Mars's orbit. At this point, it will be traveling at its maximum velocity of 68 kilometers per second. The comet will make its closest approach to Earth on December 19, 2025, though it will remain at a safe distance of 167 million miles. Throughout this journey, 3I/Atlas poses absolutely no threat to Earth. Its trajectory ensures it will pass safely through our solar system before continuing its eternal voyage into interstellar space.
The oldest comet in the universe.
So perhaps the most astounding aspect of 3I/Atlas is, honestly, just its incredible age. Research led by Matthew Hopkins at Oxford University suggests this interstellar visitor could be between 7.6 and 14 billion years old. potentially older than our entire solar system by more than 3 billion years. The key to understanding its ancient origins lies in its velocity and trajectory. With a hyperbolic excess velocity of 58 kilometers per second, 3I/Atlas is moving way faster than objects typically ejected from nearby star systems. This extreme speed suggests it originated from the Milky Way's thick disk, a region containing some of the galaxy's oldest stars, most of them over 10 billion years old. Professor Chris Lintott, co-author of the Oxford study and presenter of BBC's The Sky at Night, explains the significance. This is an object from a part of the galaxy we've never seen up close before. We think there's a 2/3 chance this comet is older than the solar system, and that it's been drifting through interstellar space ever since. If confirmed, 3I/Atlas would represent a pristine time capsule from the early universe, carrying materials that formed when the galaxy was young and star formation was just beginning.
Global telescope network mobilizes.
The discovery of 3I/Atlas has, well, triggered an unprecedented global observational campaign. Astronomers all around the world are pointing every available telescope at this rare visitor, knowing they've got only months before it disappears forever into the depths of space. The James Webb Space Telescope, with its massive 21.3-foot mirror and incredible infrared sensitivity, is perfectly positioned to study 3I/Atlas in detail. Webb can detect heat signatures and identify specific chemicals and minerals on the comet's surface, potentially revealing its composition and origin. The Hubble Space Telescope complements Webb's capabilities with its ultraviolet observations, providing a complete picture across different wavelengths of light. Ground-based observatories from Hawaii to Chile to South Africa are tracking the comet's movement, measuring its brightness changes, and analyzing the faint light it reflects. The European Space Agency is actively monitoring the object through multiple facilities, while the Instituto de Astrofísica de Canarias has contributed crucial observations using their Atlas-TD telescope and the Gran Telescopio Canarias. Radio telescopes like the Very Large Array in New Mexico are also listening for any unusual emissions as the comet interacts with the solar wind, making sure no potential signals are missed during this historic encounter. Comparing interstellar visitors. 3I/Atlas joins, an exclusive club of confirmed interstellar objects, each with unique characteristics that really challenge our understanding of the cosmos. The first visitor, 1I/Oumuamua, discovered in October 2017, remains the most mysterious. Its cigar-like or pancake flat shape and unexplained acceleration as it left our solar system sparked intense debate, with scientists like Avi Loeb even suggesting it might be artificial technology. The second visitor, 2I/Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov, behaved more like a familiar comet with a visible tail and composition similar to comets in our solar system. Its nucleus was estimated at just 400 meters across, making it relatively small compared to 3I/Atlas. What sets 3I/Atlas apart is its combination of size, age, and clear cometary behavior. While Oumuamua showed no outgassing and Borisov was relatively young, 3I/Atlas displays active cometary features despite potentially being billions of years old. Its orbital eccentricity of 6.15 far exceeds both predecessors, indicating it's traveling much faster and likely originated from a more distant region of the galaxy. This progression from mysterious to familiar to ancient suggests interstellar objects are more diverse than we initially thought.
Clues to galactic chemistry and life.
While the composition of 3I/Atlas could, really revolutionize our understanding of how planets form throughout the galaxy. Early observations have detected a reddish coma surrounding the comet, which is actually pretty similar to what was seen in 2I/Borisov. This red coloration most likely comes from organic-rich dust containing these complex molecules called tholins, carbon-based compounds that scientists believe played a crucial role in the origin of life. If 3I/Atlas contains materials similar to comets in our own solar system, it would provide pretty powerful evidence that the building blocks of life are widespread throughout the galaxy. The presence of water ice, organic compounds, and complex chemistry would suggest that the ingredients for life aren't unique to Earth, but are actually common products of stellar evolution. On the other hand, if the comet's composition turns out to be entirely different from anything in our solar system, it would reveal the incredible diversity of conditions under which planetary systems can form. This could mean that 3I/Atlas formed around a star with different metallicity, or in a region of space with really unique chemical conditions. Either outcome would be scientifically revolutionary, either confirming the universality of life's ingredients or revealing new pathways for chemical evolution in the cosmos. Mysteries and unanswered questions. Mysteries and unanswered questions. Despite intensive observations, 3I/Atlas guards many secrets that continue to puzzle astronomers. One of the biggest mysteries is its exact size and rotation. While early estimates suggest a nucleus between 10 and 20 kilometers across, the active coma of gas and dust makes precise measurements challenging. Some observations suggest the comet might be tumbling chaotically rather than spinning smoothly, possibly indicating a violent past collision or gravitational encounter. The comet's unusual brightness remains another puzzle. Its high reflectivity could indicate a surface composition unlike anything in our solar system, or it might be experiencing an outburst that temporarily increases its brightness. Understanding this brightness is crucial for determining its true size and nature. As with previous interstellar visitors, some scientists are monitoring 3I/Atlas for any signs of non-gravitational acceleration, movement that can't be explained by gravity alone. While such acceleration is normal for comets due to outgassing, any unusual patterns could provide clues about the comet's internal structure or composition. The question of artificial origin, while highly unlikely, remains part of the scientific discussion. Avi Loeb has suggested using advanced telescopes to search for any signs of technology, though natural explanations are far more probable.
Future missions and rapid response.
Future missions and rapid response. The discovery of 3I/Atlas has accelerated discussions about rapid response missions to intercept future interstellar visitors. While this comet was discovered too late for any spacecraft to reach it, several space agencies are developing concepts for quick launch missions that could be deployed when the next interstellar object is detected. The European Space Agency's Comet Interceptor mission, scheduled for 2029, represents one approach to studying pristine comets. While originally designed for objects from our solar system, similar technology could be adapted for interstellar targets if sufficient warning time exists. The upcoming Vera C. Rubin Observatory will revolutionize interstellar object detection when it begins operations. Its enormous camera will photograph the entire visible sky every few nights, creating a movie of the cosmos that should detect multiple interstellar objects annually. Astronomers predict it might discover between 5 and 50 interstellar visitors during its 10-year legacy survey of space and time. This improved detection capability means future interstellar objects might be spotted months or even years before their closest approach, providing sufficient time to plan and launch intercept missions. Such missions could return samples from other star systems, bringing pieces of alien worlds directly to Earth for analysis.
A new era of interstellar archaeology.
A new era of interstellar archaeology. 3I/Atlas represents more than just another astronomical discovery. It marks the beginning of interstellar archaeology, the study of physical artifacts from other star systems. Each interstellar visitor carries information about distant worlds we may never visit, providing direct samples of materials that formed under completely different conditions than those in our solar system. The rapid succession of interstellar discoveries, 3 confirmed objects in less than a decade after centuries of seeing none, suggests these cosmic wanderers are far more common than previously thought. This frequency implies that planetary systems throughout the galaxy routinely eject material into interstellar space, creating a vast network of cosmic debris that connects star systems across the galaxy. As our detection capabilities improve and more interstellar objects are discovered, we'll begin to understand the diversity of planetary formation processes throughout the Milky Way. Each visitor provides a unique data point about stellar chemistry, planetary evolution, and the conditions that exist in different regions of our galaxy. 3I/Atlas, with its ancient age and pristine composition, offers a particularly valuable glimpse into the early universe, when the first generation of planets was forming around young stars billions of years ago. From its discovery in the Chilean desert to its journey through our solar system, 3I/Atlas has already transformed our understanding of interstellar visitors. This ancient comet, potentially older than our solar system itself, carries secrets from the early universe that could reshape our knowledge of planetary formation and the ingredients for life. As it continues its eternal voyage through the cosmos, 3I/Atlas reminds us that our solar system isn't isolated but part of a vast galactic community. Thanks for watching Stellar Tech, and don't forget to subscribe for more cosmic discoveries. Imagine a moment when humanity's most powerful machine briefly created a microscopic black hole, a tiny tear in the fabric of space-time itself. This happened not in some distant galaxy but right here on Earth, deep beneath the Swiss-French border at CERN's Large Hadron Collider. In recent years, scientists have observed phenomena that could represent the birth and evaporation of micro-black holes, discoveries that challenge our understanding of physics, extra dimensions, and the very nature of reality. Today we dive into what happened after CERN scientists created these quantum black holes.
The machine that recreates the Big Bang.
The Large Hadron Collider at CERN stands as humanity's most ambitious scientific instrument, a 27-kilometer ring of superconducting magnets buried 175 meters beneath the France-Switzerland border near Geneva. Built between 1998 and 2008 through collaboration with over 10,000 scientists from hundreds of universities across more than 100 countries, the LHC represents the pinnacle of human engineering achievement. This massive machine accelerates protons to 99.9999991% of light speed, creating collision energies of up to 13 tera-electron-volts. Conditions that haven't existed in our corner of the universe since moments after the Big Bang. The LHC's primary mission involves exploring fundamental physics through these extreme energy collisions, most famously leading to the discovery of the Higgs boson in 2012, which confirmed how particles acquire mass. The collider features 4 main crossing points where accelerated particles collide, surrounded by massive detectors like ATLAS and CMS that track the spray of particles created in these violent encounters. These detectors, built like giant 3-dimensional cameras made of millions of sensors, can capture the fleeting signatures of exotic particles that exist for mere fractions of a second.
The theory behind microscopic black holes.
The possibility of creating microscopic black holes at the LHC emerges from revolutionary theories involving extraspatial dimensions beyond our familiar 3. Models proposed by physicists Nima Arkani Hamed, Savas Dimopoulos, and Gia Dvali, known as the ADD model, suggest that gravity might propagate through additional hidden dimensions, while other forces remain confined to our 3-dimensional space. These theories attempt to solve the hierarchy problem, why gravity appears so much weaker than other fundamental forces. A tiny refrigerator magnet can overcome Earth's entire gravitational pull, suggesting gravity's apparent weakness might result from it spreading through extra dimensions we cannot perceive. If these extra dimensions exist, they would dramatically lower the energy required to create black holes from an impossible 10 to the 19th giga-electron volts down to potentially just a few tera-electron volts. Precisely the energy range the LHC can achieve. Under these conditions, when protons collide at nearly light speed, they could concentrate enough energy within a tiny region to exceed the Schwarzschild radius, causing spacetime to collapse into a microscopic black hole. According to Stephen Hawking's theory, such micro-black holes would be extraordinarily unstable, evaporating almost instantly through quantum radiation in roughly 10 to the minus 27 seconds while releasing distinctive particle signatures.
The hunt for quantum black holes.
The CMS and ATLAS experiments at CERN have conducted extensive searches for microscopic black hole signatures in proton-proton collisions. These searches focus on identifying the distinctive particle sprays that would result from Hawking radiation as micro-black holes evaporate almost instantaneously after formation. The CMS experiment completed comprehensive searches for microscopic black holes produced in high-energy collisions, analyzing data for the characteristic patterns these exotic objects would create. Their detectors look for events where particles converge inward rather than spray outward, consistent with space-time being warped by extreme gravity before the black hole's rapid evaporation. Recent ATLAS collaboration research published in 2023 searched for quantum black holes in electron plus jet and muon plus jet invariant mass spectra using 140 inverse femtobarns of collision data. While no definitive evidence was found, the experiment set important limits on black hole production, ruling out their existence below certain mass thresholds in various theoretical models. The search techniques involve sophisticated pattern recognition algorithms that can distinguish genuine black hole signatures from the background noise of ordinary particle collisions. These advanced analysis methods continue to push the boundaries of what's detectable, bringing scientists closer to potentially revolutionary discoveries. Hawking radiation and instant evaporation. Stephen Hawking's groundbreaking 1974 theory predicted that black holes aren't completely black but actually emit radiation due to quantum effects near their event horizons. This process, which we call Hawking radiation, happens when quantum fluctuations create particle-antiparticle pairs right at the black hole's boundary. One particle falls in, while the other escapes. Now, for microscopic black holes, this evaporation process happens almost instantaneously. The smaller the black hole, the more intense its Hawking radiation and the faster it evaporates. A micro-black hole created at the LHC would exist for about 10 to the minus 27th seconds, an almost incomprehensibly brief moment during which light can barely travel the width of a single proton. During this fleeting existence, the black hole would release its entire mass energy as a burst of particles, creating a distinctive signature that, in principle, sophisticated detectors could potentially observe. The evaporation would produce a specific spectrum of particles including quarks, gluons, photons, and possibly even some exotic particles not found in the standard model. This rapid evaporation ensures that any micro-black holes created at CERN would be completely harmless, disappearing long before they could interact with surrounding matter or, grow larger through accretion. Evidence for extra dimensions. The detection of micro-black holes would provide, honestly, the first experimental evidence for extraspatial dimensions, fundamentally revolutionizing our understanding of reality's structure. The Arkani-Hamed-Dimopoulos-Dvali model and Randall-Sundrum scenarios propose that our universe contains additional spatial dimensions beyond the three we experience directly. These hidden dimensions would be compactified, curled up so tightly at every point in space that we just can't perceive them in everyday life. Imagine for a second an ant walking along a garden hose. From far away the hose looks one-dimensional, but up close, the ant can move around its circumference through an extra spatial dimension. If gravity propagates through these extra dimensions while electromagnetic weak and strong forces remain confined to our familiar three-dimensional space, it would explain why gravity appears so much weaker than the other fundamental forces. The precise energy threshold for micro-black hole production would actually reveal the number and size of these extra dimensions. Recent theoretical work suggests that observing micro-black hole evaporation patterns could provide detailed information about the geometry of extra dimensions, potentially mapping aspects of reality that have remained hidden since the universe's beginning. This would represent, without exaggeration, one of the most profound discoveries in the history of physics. The search continues with advanced technology. CERN's search for micro-black holes employs, honestly, some of the most cutting-edge detection technology and analysis techniques that really push the boundaries of experimental physics. The ATLAS and CMS detectors surrounding collision points contain millions of sensors arranged in layers, creating three-dimensional snapshots of particle interactions with unprecedented precision. Machine learning algorithms now analyze collision data, searching for subtle patterns that might indicate micro-black hole formation and evaporation. These AI systems can process vast amounts of data far more efficiently than human researchers, identifying anomalies that might otherwise be missed in the background noise of ordinary particle collisions. The CMS experiment's search for microscopic black holes has set increasingly stringent limits on their production, ruling out their existence up to masses of 3.5 to 4.5 TeV in various theoretical models. Similarly, ATLAS collaboration research has pushed these limits even higher, with recent studies excluding quantum black holes below 9.2 TeV in the ADD model and 6.8 TeV in the Randall-Sundrum model. As the LHC undergoes upgrades toward its high luminosity phase, planned to begin operations in the late 2020s, the increased collision rate and improved detector sensitivity will provide even more opportunities to search for these elusive quantum phenomena. Connections to dark matter and dark energy. The potential discovery of micro-black holes at CERN could, really illuminate the mysterious dark sector of physics which actually makes up about 95% of the universe's content. Dark matter and dark energy are still, among the greatest unsolved puzzles in cosmology, and we can only detect them through their gravitational effects on visible matter and the expansion of the cosmos. Some theoretical models even suggest that black hole evaporation might produce particles from the dark sector, which would offer us a unique laboratory window into these invisible components of the universe. If micro-black holes briefly connect our familiar matter with dark matter through quantum effects, then their evaporation signatures could finally reveal the nature of particles that have managed to elude direct detection for decades. Now, primordial black hole theories propose that tiny black holes formed in the early universe could account for some or maybe even all of dark matter. If CERN's experiments are able to produce micro-black holes with evaporation patterns that match theoretical predictions for primordial black holes, that would be honestly pretty compelling evidence for these cosmological models. Additionally, some theories suggest that dark energy's mysterious acceleration of cosmic expansion might be connected to extra dimensions through which gravity propagates. So, micro-black hole production could, in fact, offer indirect evidence for these connections, potentially solving multiple cosmic mysteries at once through a single experimental breakthrough. Quantum entanglement and space-time connections. The creation and evaporation of micro-black holes provides a unique testing ground for the revolutionary ER equals EPR conjecture, which was proposed by physicists Juan Maldacena and Leonard Susskind back in 2013. This groundbreaking idea suggests that quantum entanglement and wormholes, also known as Einstein-Rosen bridges, are actually the same phenomenon, just viewed from different perspectives. According to this theory, when particles become quantum entangled, they're actually connected through these tiny wormholes in the fabric of space-time itself. If micro-black holes form at CERN, their evaporation could produce entangled particles that reveal these quantum connections, potentially providing the first experimental evidence for this profound relationship between quantum mechanics and general relativity. Observing correlated particle decays from micro-black hole evaporation could demonstrate that space-time isn't really the fundamental backdrop against which physics happens, but rather something that emerges from deeper quantum information relationships. This would suggest that the fabric of reality is woven from quantum threads of information, instead of being a smooth, continuous medium. Discoveries like this could address the black hole information paradox, which is this really fundamental problem where quantum mechanics and general relativity seem totally incompatible at black hole boundaries. The data from micro-black hole evaporation might finally reveal whether information falling into black holes is truly lost, or somehow preserved in their radiation. Safety and cosmic ray comparisons. Concerns about creating black holes at the LHC have been thoroughly addressed through comprehensive safety assessments by independent groups of physicists all over the world. The fundamental argument for safety comes from comparing LHC energies with natural cosmic ray collisions that constantly bombard Earth's atmosphere. Cosmic rays from space carry energies up to 10 to the power of 20 electron volts, which is about 10 million times higher than the LHC's maximum energy of 13 tera-electron volts. These ultra-high energy particles create natural collisions with our atmosphere roughly 1 million times per square kilometer every year, and Earth has experienced this kind of bombardment throughout its 4.5 billion year history without any damage at all. If micro-black holes could pose any danger at the energies CERN explores, nature would have already conducted these experiments countless times throughout cosmic history. The fact that Earth and other astronomical objects remain completely intact demonstrates that such phenomena are either impossible or totally harmless. Even if micro-black holes formed but didn't evaporate through Hawking radiation, which would mean Hawking's theory is fundamentally wrong, they would still pose no threat, thanks to their incredibly weak interaction with ordinary matter. They would just pass right through Earth almost without effect, similar to the trillions of neutrinos that pass through our bodies every second, unnoticed. The future of fundamental physics. The potential discovery of micro-black holes at CERN represents a lot more than just confirming some exotic theoretical predictions. It would actually mark the beginning of a whole new era in fundamental physics research. Such discoveries would provide the first experimental access to quantum gravity, the long-sought theory that unifies quantum mechanics with Einstein's general relativity. Understanding how gravity behaves at quantum scales could, honestly, revolutionize technology in ways we can barely even imagine, maybe leading to new forms of energy generation, propulsion systems, or even manipulation of space-time itself. The knowledge gained from studying micro-black hole evaporation could also inform our understanding of the universe's earliest moments, as well as its ultimate fate. As CERN prepares for the high-luminosity LHC upgrade and looks ahead to even more powerful future colliders, the search for micro-black holes will continue with unprecedented sensitivity and precision. Every single collision brings us closer to potentially revolutionary discoveries that could reshape our understanding of reality's most fundamental nature. The journey into quantum gravity and extra dimensions is humanity's boldest exploration of the cosmos, probing the deepest mysteries of existence through the power of human ingenuity and international scientific collaboration. Whether or not micro-black holes actually exist, the search itself advances our knowledge of the universe's most profound secrets. CERN's quest to create and study micro-black holes really does represent humanity's boldest attempt to understand the fundamental nature of reality itself. Whether these quantum phenomena exist or not, the search has already pushed forward our knowledge of particle physics, extra dimensions, and those deep connections between quantum mechanics and gravity. As scientists keep pushing the boundaries of what's possible, we're standing on the threshold of discoveries that could transform our understanding of space, time, and matter forever. Thanks for watching Stellar Tech, and don't forget to subscribe for more groundbreaking discoveries from the frontiers of science. The moon, long thought to be a silent, inactive rock, is now revealing secrets that could change everything we know about our closest celestial neighbor. Renowned physicist Michio Kaku has issued a warning after NASA detected a mysterious seismic signal deep within the moon's core. This discovery challenges decades of assumptions and hints at dynamic processes that might even impact Earth over geological timescales. Today, we explore what this seismic activity means for lunar science, future missions, and our understanding of planetary evolution.
The moon's hidden activity revealed.
For decades, scientists believed the moon was geologically dead, its core solidifying and cooling quietly like a dying ember in space. But recent data from NASA's lunar sensors have detected unexpected seismic pulses emanating from deep within the moon's interior, challenging everything we thought we knew about our celestial companion. These signals suggest the moon's core is not just passively cooling, but undergoing significant changes that could reshape our understanding of lunar evolution. Physicist Michio Kaku has highlighted these findings in recent lectures, warning that the moon's internal activity could have long-term effects on its structure and even Earth's environment over geological timescales. This seismic activity challenges the traditional view of the moon as a static, inert body that finished its geological story billions of years ago. The discovery represents a paradigm shift in lunar science, forcing researchers to reconsider fundamental assumptions about how small planetary bodies evolve and die in our solar system.
Inside the moon's dynamic core structure.
The moon's internal structure resembles a miniature version of Earth's, with a solid inner core surrounded by a partially molten outer core that scientists are now discovering remains more active than previously thought. New analyses estimate the inner core's radius at approximately 240 kilometers, primarily composed of iron and nickel, enveloped by a fluid outer core extending roughly 350 kilometers from the moon's center. Geological evidence from lunar rocks brought back by Apollo missions shows the moon once possessed a magnetic field generated by its core, similar to Earth's protective magnetosphere. This ancient magnetic field, which existed billions of years ago, gradually faded as the core cooled and solidified. However, recent seismic data suggests the core might still be active in subtle but measurable ways. The core's structure includes a partial melt layer at the base of the lunar mantle, approximately 150 kilometers thick, which sits above the liquid outer core. This complex internal architecture indicates that the moon's interior remains more dynamic than the simple cooling model previously accepted by planetary scientists.
Apollo's legacy and modern seismic discoveries.
NASA's Apollo missions first placed seismometers on the moon between 1969 and 1977, with the Apollo 11 passive seismic experiment marking humanity's first attempt to listen to another world's internal activity. These instruments detected moonquakes and revealed some internal activity, recording about 100 to 200 meteorite impacts during their operational lifetime and detecting several categories of seismic events. However, the resolution of those 1970s instruments was limited by the technology available at the time. The Apollo seismometers operated until September 1977, providing valuable but incomplete data about lunar seismic activity. Now, with advanced sensors and modern analysis techniques, scientists are uncovering new categories of seismic events that were previously undetectable. These include deep moonquakes caused by tidal forces with Earth, shallow quakes with tectonic origins, and thermal quakes caused by extreme temperature fluctuations between lunar day and night. The new data suggests the moon's interior is more dynamic than once thought, with ongoing processes that continue to shape its internal structure even today.
The shrinking moon theory and tectonic activity.
One of the most intriguing hypotheses emerging from recent research is that the moon is slowly shrinking as its core continues to cool and solidify over geological time. This gradual contraction causes stress in the brittle lunar crust, leading to the formation of tectonic ridges, fault lines, and surface scarps that are surprisingly young in geological terms. Recent studies have identified hundreds of previously unknown ridges on the moon's surface, some of which may have formed as recently as 200 million years ago, a blink of an eye in geological terms. Using advanced mapping techniques and crater counting methods, scientists determined that these small ridges are younger than other features in their surroundings, meaning the moon's crust is still shifting and evolving today. This slow contraction and associated seismic activity could explain the mysterious seismic pulses detected recently, suggesting the moon is still adjusting internally as it continues its billion-year cooling process. The discovery challenges the long-standing belief that the moon became geologically dormant billions of years ago, and suggests that internal forces are still shaping its surface in measurable ways.
Earth-Moon gravitational dance and climate implications.
The implications of the moon's internal activity extend far beyond lunar science, potentially affecting Earth's long-term climate stability and orbital dynamics. The moon's gravitational influence stabilizes Earth's axial tilt at 23.5 degrees, which regulates our seasons and prevents chaotic climate swings that would make complex life difficult to sustain. Changes in the moon's mass distribution due to core activity and internal restructuring could subtly affect this crucial gravitational relationship over timescales of millions of years. While these effects are not immediate or catastrophic, they could influence Earth's climate cycles, tidal patterns, and even the Milankovitch cycles that govern ice ages over geological epochs. Michio Kaku has emphasized that the moon acts like a cosmic stabilizer, preventing Earth from wobbling chaotically like other planets of similar size. This stability has allowed for the slow, steady development of ecosystems and eventually human civilization. The moon's gravitational pull creates not just ocean tides, but also slight bulges in Earth's crust, generating heat through friction that contributes to our planet's internal warmth and geologic activity.
Next-generation lunar seismic monitoring.
NASA is preparing to deploy revolutionary new seismic instruments on the moon as part of upcoming Artemis missions, representing a quantum leap forward in our ability to monitor lunar internal activity. The Farside Seismic Suite, scheduled to land in Schrödinger Basin around 2026, will be the first seismic station placed on the moon's far side since the Apollo era. These next-generation seismometers will be approximately 30 times more sensitive than Apollo-era equipment, capable of detecting ground motions smaller than a single hydrogen atom. The Very Broadband Seismometer, originally designed for Mars InSight mission, represents the most sensitive seismometer ever built for space exploration. Additionally, the Lunar Environment Monitoring Station will establish a long-duration seismic station near the South Pole, where NASA's Artemis missions plan to build a permanent human presence. Unlike Apollo instruments that operated for limited periods, these new systems are designed to continuously monitor lunar seismic activity for months or even years, providing unprecedented insights into the moon's internal dynamics.
AI revolutionizes Apollo-era data analysis.
Artificial intelligence is playing, a crucial role in revolutionizing our understanding of lunar seismic activity by analyzing decades-old Apollo data with unprecedented precision. It's like machine learning algorithms are detecting patterns and anomalies in the original seismic recordings that human analysts missed or dismissed as noise during the 1970s analysis. These sophisticated AI systems can distinguish between genuine lunar activity and instrument artifacts with remarkable accuracy, flagging seismic events that didn't fit expected patterns and were often filtered out as measurement errors decades ago. NASA scientists describe this process as revolutionary, comparing it to having a conversation with someone for 50 years and suddenly realizing you've been missing half of what they've been saying. The AI analysis has revealed entire categories of seismic events occurring beneath the lunar surface that were completely missed by previous analysis techniques. These aren't just minor tremors but signatures of complex processes happening in the moon's core that provide new insights into its internal structure and ongoing geological activity. This technological breakthrough is helping scientists reconstruct a completely new picture of the moon's internal dynamics and the seismic pulse that has drawn Michio Kaku's attention.
Lunar exploration safety and future mission planning.
So, the discovery of ongoing seismic activity on the moon, well, it really raises some critical safety considerations for future lunar exploration and colonization efforts. Human missions and those mining operations planned near the lunar South Pole, they've got to carefully consider the risks posed by tectonic activity and potential moonquakes that could damage habitats or endanger astronauts. Understanding fault zones and stress patterns is just essential if we want to ensure the safety and stability of lunar habitats and infrastructure. Unlike Earth, the moon's crust doesn't have water circulation to heal cracks naturally, so once we fracture its brittle surface through mining or construction, those fractures could stick around and potentially trigger even larger seismic events. NASA's upcoming seismic networks will be absolutely vital for mapping these geological hazards and guiding mission planning for the Artemis program. The lunar regolith, which is that layer of loose material covering the moon's surface, actually sits atop a pretty complex network of faults and stress zones that could be disturbed by human activity. Future lunar bases are going to be completely dependent on their structural integrity, making seismic monitoring crucial for astronaut safety, and a habitat breach caused by unexpected seismic activity could be catastrophic, exposing crew members to the vacuum of space with very little warning or opportunity for evacuation.
A rare cosmic window for scientific discovery.
Michio Kaku emphasizes that humanity exists in a rare cosmic window, a fleeting moment in astronomical time when the moon's internal activity is still detectable before it eventually ceases forever. In another billion years or so, the moon's core may freeze solid completely, ending the geological processes we can observe today. This unique opportunity allows scientists to study planetary evolution processes that happen over billions of years, providing insights that, honestly, can't be obtained any other way. The moon is pretty much giving us a live demonstration of how small planetary bodies evolve and eventually become geologically inactive, serving as a sort of natural laboratory for understanding planetary death. Insights gained from studying the moon's core activity can inform our understanding of other rocky bodies in the solar system and beyond, including potentially habitable exoplanets. By watching the moon transition from a molten core to a solid one, scientists gain crucial insights into how different-sized worlds evolve, whether they can maintain protective magnetic fields, and their potential for supporting life. Kaku explains that we're incredibly fortunate to exist at exactly the right moment to witness the final chapters of the moon's geological story.
The moon as a key to planetary evolution.
The moon's seismic signals represent far more than just scientific curiosities. They're actually fundamental keys to understanding planetary life cycles throughout the universe. As the moon's core continues to cool and solidify, it offers researchers an unprecedented live demonstration of how small planetary bodies evolve and eventually die, providing crucial data for planetary science models. This knowledge is particularly vital as humanity prepares to return to the moon and establish a permanent presence there. Understanding the moon's internal processes helps scientists identify potentially habitable exoplanets and predict how their geological evolution might affect their ability to support life over billions of years. The moon serves as an intermediate step in planetary development, larger than asteroids but smaller than Earth-like planets, giving us really important insights into how different-sized worlds evolve. By studying how the moon's core solidifies and loses its magnetic field, scientists can develop models that predict how long smaller rocky exoplanets might maintain their protective magnetic shields. Michio Kaku's warning reminds us that the moon still holds secrets that could totally reshape our understanding of planetary science, Earth's future, and our place in the cosmic neighborhood. The moon is no longer the silent, dead rock we once thought it was. Thanks to new seismic discoveries and Michio Kaku's warnings, we now know it's a dynamic world with an active interior that could even influence Earth itself. As we prepare to return and explore further, understanding these internal processes is more important than ever before. Stay tuned for more updates on lunar science and the future of space exploration. Thanks for watching Stellar Tech, and don't forget to subscribe for more cosmic insights.